Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Probability, the Addition Rule, and the Rule of Complements. As always, be an active learner as you watch these videos. Two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. If we look at this Venn diagram, we see a set E that contains 0, 1, and 2, a set F that contains 8 and 9, and outside of E and F, there are 3, 4, 5, 6, and 7. So S is the universal set, and these two sets are disjoint. Now note that the outcomes in E are inside circle E and the outcomes of F are inside F. And all outcomes in the sample space that are not in E and F are outside the circle. So what we have is that the probability of E is the number of elements in E divided by the number of elements in S, which is 3 out of 10 or 0.3. Similarly, the probability of F is the number in F divided by the number in the sample space, which is 2 out of 10 or 0.2. In addition, if we say what's the probability of being in E or F, I just add the 2 because there are 5 numbers that are in here, so it's 5 over 10 equal 0.5. This result occurs because of what we call the addition rule for disjoint events, which states if E and F are disjoint or mutually exclusive events, then the probability of E or F is equal to the probability of E plus the probability of F. This addition rule for disjoint sets can be extended to more than 2 events. That would be that the probability of E or F or G or ... is equal to the sum of the probabilities as long as these are all disjoint events. And here you can see an example with 3 events. So the probability of E is going to be, again, 3 out of 10. The probability of G is going to be 2 out of 10. And the probability of F is going to be 2 out of 10. And so the probability of being in 1, E, or F, or G is equal to the sum of the probabilities because they are disjoint events. So you add them up and you will get 0.7. Let's consider a more sophisticated example that's called Binfords law. Our number system consists of digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And because we have a convention of not writing 12 as 0, 1, 12, the first significant digit in any number has to be 1 through 9. So we can think of each digit appearing with equal frequency. You might think that, but people have looked at the data, namely these people, and they realize that things don't happen that way. One happens much more often, and I think that's in a sense because little numbers are more common than big numbers. But anyway, we have the following results that have become known as Binfords law. So the digit 1 in the world appears with probability 0.30. 2 appears with 0.176, 3 appears with 0.125, 4 appears with 0.097, and so on and so forth. So these are the ways which they appear. Now, one of the things we're asked to do in this, we're supposed to verify that Binfords law is a probability model. And that means do these things add up to 1? Well, if we add up all the numbers, we do get 1. You could do this on an Excel spreadsheet if you wanted. And all the numbers are bigger than or equal to 0. And that means because we have those two laws, this is a probability model. Now, we can use Binfords law to determine the probability that a randomly selected first digit is either 1 or 2. Well, it's either 1 or 2. Those are disjoint events. It can't be both. So what I'm going to do is the probability of 1 or 2 is the sum of the two by our addition rule, and that is going to be 0.477. And similarly, they say use Binfords law to determine the probability that the first digit is at least 6. Now, at least 6 means that's like you have to be at least 21 to drink legally in the state of Illinois. That means you have to be 21 or over, so at least 6 means 6, 7, 8, or 9. Now these again are disjoint events because either you begin with a 6 or a 7 or an 8 or a 9, and those four items don't overlap with any. So then the probability of at least 6 is the probability of 6 or 7 or 8 or 9. You add them up and you get 0.222. And so if we looked at 100 numbers, we would expect that around 22 would begin with 6, 7, 8, or 9. We can also do problems like this with cards. This is the deck of cards. So here we have spades, hearts, clubs, and diamonds. So compute the probability of drawing a king if we draw a single card. Well, there are 52 cards, and so drawing a king, there are 4 kings out of 52, so that is 1 out of 13. Another question could be, compute the probability of drawing a king or drawing a queen. Or drawing a jack, so drawing one of the 3. Now, you don't draw a queen if you draw a king, and so on and so forth. These are all disjoint events, so you add them together, and so that would be 3 out of 13 is the probability of a king or a queen or a jack. Now, sometimes the sets are not disjoint and the rule reads differently then. So consider this case where we have a set E and a set F, but the sets are overlapping with the elements of 1 and 3. Now, these are disjoint sets here. So this part that is shown green, this part that's shown with 1, 3, and this part that's just 0, 2, 4 are 3 disjoint sets. So if I added those together, I would get the probability of E or F. But if I take the probability of E, I would add this part in. The probability of F would add this part in, and so I would be double counting this. So the probability of E or F can be found by the probability of E, which is 5 out of 10, plus the probability of F, which is 5 out of 10, and we subtract off those elements that are in E and F, and so that will be the probability of E and F is minus 2 over 10. So this would be 1 minus 2 over 10 is going to be 8 over 10, or in lowest terms, 4 over 5. Now that agrees with our counting, and in fact here's the generalization of that, and this is for any 2 events, E and F. They do not have to be disjoint for this to be true. The probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F, where they overlap. So let's look at an example of this. So here's a problem where we're supposing that a single card is selected from a standard 52 card deck, the one that we looked at earlier. Compute the probability of the event E, drawing a king, or F, drawing a diamond. Well, so we're talking about drawing a king or drawing a diamond. Now these events are not disjoint because you can draw a king that is also a diamond, the king of diamonds. And so we're going to use the general addition rule, which we just read, but it says that the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. Now, the probability of getting the king of diamonds, that's just 1 out of 52. The probability of getting a diamond, 1/4 of the cards are diamonds, or 13 out of 52, and the probability of getting a king is, there are 4 kings out of 52. So you add these two numbers and subtract this fraction, put your answer in lowest terms, and you get 4 out of 13. Let's consider again an example, and this example is a contingency table and shows the marital status of males and females 15 years older in the United States. And these are in terms of millions of units. So never married, we have these numbers. Married, we have these numbers. Widowed, we have these numbers. Divorced, we have these numbers. And separated, we have these numbers. And this, of course, is a contingency table. We have males and female data. And so what we're going to do is we're going to look at this table, and just to describe something here, if we say what's the probability that males were never married, or how many people are there, well, you would look at married and males, and there would be 63.3 million males that are married. Okay, but we're going to use this contingency table to answer these questions. So determine the probability that a randomly selected U.S. resident or 15 years or older is male. Well, you say, what is the number of males divided by the total number? Now you have to add up this column to do that. But if we add up that column, we can use Excel to do that, we find that there are 126.9 million males 15 years or older, and there are total in this survey of 260.1 million U.S. residents 15 years or older. So the probability is going to be the size of the males divided by that, and we find that just a little less than half, or 48.8% of this survey were males. Let's look at another problem. Determine the probability that a randomly selected U.S. resident is widowed. Now, if we look at the number of people who are widowed, it's the sum of these two rows, the sum of these two columns, because you can be male or female. And so that means that there are going to be 15.2 million U.S. residents that are widowed. That's divided by the grand total, which was 260.1, and we will get, as that calculation, that there's almost a 6% chance of, if you pick someone at random, them being widowed. Now, let's look at another one. Determine the probability that someone randomly selected from this table is widowed or divorced. Now, widowed or divorced. Now, the events widowed and divorce are disjoint because you had to pick one or the other. We put people into one of these categories or the other, so they are disjoint. But now we're using the addition rule. And I realized that in the real world you could say, oh, someone was widowed, then they got married again, and then they got divorced. But that's not the question that was asked here. They asked the question differently, and so these are disjoint events. So probability of widowed or divorced is the probability of widowed plus the probability of divorced. Again, we can get these numbers from the table, and we find out that almost 17% are widowed or divorced. And the last question that we talk about in this example is determine the probability that someone selected is male or widowed. Now here, male and widowed are not disjoint, so we have to use the general rule. So the probability of male or widowed is the probability of male plus the probability that you're widowed minus the probability you're male and widowed. And so we add those probabilities and we subtract male and widowed, and male and widowed, here's male and widowed is 3.3 over that. We do the calculation and we get that that is almost, that's a little bit over 50%. It's 53.4%. We now turn our attention to computing the probability of an event using the complement rule. Sometimes it is easier to calculate the probability of an event by considering the complement. Let's begin by talking about what does it mean to talk about the complement of event E. The complement of an event is defined this way. Let S denote the sample space of probability experiment and E denote an event. The complement of E denoted by E, and that's like a little exponent C, is an outcome in the sample space that are not outcomes in the event E. Here's a picture. So here we have the universal set. E is inside and E complement is outside. Notice that E and E complement are disjoint events. That means that the probability of E, or the probability of E's complement, is the probability of E plus the probability of the complement, and those have to add to 1 because those are the only two events that do span the space. And so if we subtract the probability of E from both sides, we get the complement rule. If E represents any event and E complement represents the complement of E, then the probability of E complement equal 1 minus the probability of E. In other words, for any event, either the event happens or it doesn't. So you use the complement rule when you have the probability that some event will occur and you would like to know the chances that it will not occur. If the probability of it raining was 3/4, the probability that it doesn't rain is 1/4. So here's a problem. According to the National Gaming Institute, 52% of Americans have played the lottery. What's the probability that a randomly selected American has not played the state lottery? Well, the probability of not playing the state lottery is 1 minus the probability that you played the state lottery. So it is 1 minus 0.52 equals 0.48. So the probability of a randomly selected American who has not played a state lottery is 0.48. Here's a more complicated problem. This data represents the income distribution, and so you can see that we have different slices of income here. So we could ask about various probabilities. Compute the probability that a randomly selected household earned $200,000 or more. Well, that would be this many people because you're only in one of these brackets, so it's going to be this number, and it's going to be divided by the grand total. Now you have to add this up to get the grand total, but here's what you would get. So the answer to this one is you would add up all those numbers using Excel perhaps, and you would get 8284 over 120,063, and that would be almost 7%. B says less than 200,000. Well, the easiest way to do that is by complement, because if you earn less than that, this is going to be 1 minus 2,000 or more. So the probability of less than 2,000 is 1 minus the probability of 2,000 or more. So this is 1 minus the number we found in A, which is 1 minus 0.069 equals 0.931. So that is the probability. You see, most people do earn, according to this data, less than $200,000 a year. Third question says at least $10,000. Now that means you earn more than $10,000. So that's going to be a bunch of these. Now you could just add up all of these others, but it's much easier in this case to take 1 minus the probability that you earn less than $10,000. So the probability of at least $10,000 is 1 minus the probability of less than $10,000. And again, you can see that the law of complements made that calculation much easier. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.